So when you pick a disease, for example, now let's say you pick the COVID. So what next? Like,
Yeah, the
how do
first
you
thing, yeah, the
how do
first thing you need to do is you need to understand the disease dynamics.
okay.
You need to understand the biology of the disease.
Hmm. Even as a mathematician?
You have to go and read.
Okay. I
Like,
don't believe you guys do
yeah, even as man,
that.
I have to go and look at the transmission rate, statistical method.
Okay.
But I won't deceive you. The foundation of all of that are in
Hmm.
mathematics. Like data analysis, the foundation of data analysis is
Yeah.
linear algebra, and that's what Isaac is battling with now. Linear algebra is the foundation of data science. So if
Okay.
you don't understand, I was writing a code yesterday, and most of the things I was doing there, they are linear algebra, they are
Hmm.
matrices and all of that. So, and that's the foundation of and linear algebra is mathematics, it's not
Yeah. Yeah.
statistics. So
Yeah.
yeah, so the foundation of all of this statistical thing are in mathematics of the
So,
paper. Hypothesis can fail, experiment can fail, and that doesn't mean that you should give up.
Right.
When it fails, you can change your question, but
hmm.
don't manipulate data. That's the major.
Yeah. 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 Hmm.
Research
Okay.
integrity is very. So, hi everyone, welcome to Quantum Jollof podcast. And today on our list we have Dr. Kayode Oshinubi. Dr. Kayode is an infectious disease epidemiologist with an expertise in mathematics, data analysis, computational epidemiology, and his research focuses on respiratory and mosquito-borne infection using statistical method, machine learning, mathematical modeling to inform public health responses. Dr. Kayode has over 900 citations in around 70 plus peer-reviewed journals. He has held several research positions at Oxford University, Belfast University, and the Emote Center for Infection Disease. He's currently a postdoctoral researcher at Northern Arizona University, where he's developing Bayesian frameworks for forecasting disease spread. He has also held leadership role in various international mathematical and ecological forecasting organizations. Dr. Ade, you are welcome to our podcast today. We are so glad to have you join us.
Thanks for having me. I'm glad to be here too.
Yeah.
So, the first question we have for you is, I just read your citation and stuff like that, I might have left some things behind. So I want you to share in your own words a few bio about yourself, some of the information you want us to know, and all of that.
Yeah, thank you for that question. I have background in mathematics and statistics.
Mm.
And one funny thing about my PhD is that my PhD was housed in the Faculty of Medicine, even though I'm an applied mathematician and a
Okay.
statistician. But I was in the midst of medical doctors, biologists,
Wow.
bioinformatics guys, and all of that. So, and one unique thing about me is that I'm more of a multidisciplinary person, and that's why if you look at my journey, I did my BSc in the Department of Mathematics. I did my master in the Department of Mathematics. I did my PhD in Faculty of Medicine. I'm currently housed in the School of Informatics, Computing, and Cyber System. And where I've also done research visit in Oxford, I was in the Department of Computer Science. In Bielefeld, I was in Faculty of Biology.
Wow.
In Helmholtz, I was in the biostatistics unit. So that shows my kind of interdisciplinary nature. And one thing about also, if you look at my papers, you see that it's very collaborative in nature. I'm very very collaborative person. I also had some research group before coming to this. I was in a meeting with one research group I'm heading. I'm a co-founder of Black in Mathematics, an association which is we are trying to expand. It's currently
Okay.
majorly our members are currently majorly focused Africa focused, but yeah, we are trying to expand globally. And apart from being a co-founder of that Black in Mathematics Association, I'm also heading the research arm of the association. So, and that's one of the research arm you know, and generally people write me too, and I try to bring people together, to share ideas, and that's why you will see that most people have published with Americans, Europeans, Africans, Asia, yeah, because there was a time I did a work with Kuwait researchers. So I've done. I'm very I'm very diverse, even though they don't want to hear that in the United States again. I'm very interdisciplinary person. I'm very multidisciplinary person, and yeah, I believe in inclusion. I believe in equity, and
That's quite a journey, right? You said your research is about using mathematics to like understand the spread of disease and also to mitigate them. Like, how did you come about that? Like, can
yeah,
some of us we want to be medical doctors and
yeah.
then we end up like chemistry. So how did you end up as a mathematician?
I love calculation. So, and I just I'm good at it. I just it's like it's natural for me. And then so when I wanted to go to university, I was looking at the direction of engineering, and then I said, okay, I think engineering, I was a bit advanced in age, and I said, engineering, I'll use another 5 years and all of that. Okay, let me do something mathematical related. And I did math, and I started enjoying, all these advanced courses in math, all the mathematical modeling and all of that. So I continued in that direction. And when I got to France for my PhD, in my first year, most time first year of PhD is still you are still trying to decide what you do is
Right.
work is you are still reviewing literature, and along the line, COVID started, you know. And then I said, wow, okay, we are in COVID era, but math models can predict, forecast disease spread, how can we mitigate this disease, or how can we reduce the spread? How can we inform, decisions? And those were the things that was running through my mind. And I now wrote my professor that I want to, focus, developing models that has to do with. And then I had one of my professors he had a PhD in applied mathematics, and he also has a PhD as a medical doctor. So
Oh,
he is very vast, very very vast guy, Professor Jack Dumonjo. And the second guy is a professor of statistics. So that was why I always tell everybody, I said in my PhD thesis that I did both math and statistics, because the statistics guy want me to do stat, the math guy want me to be doing math, and then also there's a biological aspect of it. So that was why my PhD thesis title was Mathematical and Statistical Modeling of Epidemic Data. So it was majorly this my core area of expertise was influenced um, by the global pandemic that happened, really, because I was not really thinking to even do math modeling. Yes, of course, I was focused on doing math modeling, but I was not looking at, okay, I want to do math modeling that's related to infectious disease. So what inspired my area of expertise now was the global pandemic that happened.
I see. So you also have because you are saying you do math and stats, many people will think they are the same. Like they are the same use of numbers, use of equations, use of
Mhm.
boring, long things. What's the difference between the two?
Yeah, they are different. Okay. Now I develop, like the model I told you, I develop a mathematical model, you
Okay.
know, but when you want to fit the model to data, you
Mm.
use statistical method. When you want to predict, when you want to
Okay.
forecast, at that point, you develop. Currently I'm developing Bayesian inference method. That's the statistical method. But the model itself can be an ODE equation, can be a mechanistic model. Of course, in statistics, there's mathematical equation. But
Okay.
yeah, of course, yeah. When you look at linear equation, it's a
Yeah.
mathematical equation. But when you
Yeah.
are analyzing it, when you are trying to define it, you start defining the predictors. That's the X.
Yeah.
You will be defining covariance. These
Mm-hmm.
are these are statistical terms. So math and stats, they are uh there's a very strong line between them where mathematics, you deal with a lot of equation, you deal with a lot of mathematical analysis, theorem, hypothesis, proofs, and all of that. When
Mm.
statistics, you work with majorly, data, you try to forecast, you try to predict, you try to do deep learning, you try to do data analysis. So these are statistics.
Okay, so I'll go with the next question. So when people hear of scientists, so we also try to communicate what science is generally at a very basic term through this podcast. So when people hear of scientists, they generally think, okay, there are people that wear white suits, uh, pipette blue liquid, because this is what they see on social media. But I can imagine that mathematics, there is no liquid. There is no need for lab coats. So there is no physical laboratory, right? You are not the typical kind of social media scientist. So if anything at all, what's your laboratory like? Do you just organize computers in the room or yeah?
Yeah, you know, most of the data we work with, they are coming from the lab.
Yeah, yeah, true.
When I visited uh, Oxford and also Emot Research Center, we're working with city values. City values are, they are laboratory values that comes from the
Mm,
lab, So even though we don't go to the lab, there's one that I'm working with now. It has, how people were tested, whether they are positive, negative, what kind of PCR test they use, and all, you understand. So even though we
mm.
don't go to the lab, we deal with all this data that comes. So we don't have wet lab. You are right.
Okay, okay.
Don't have wet lab, but sometimes I was at a workshop. I was in Atlanta some weeks back. I was at a workshop, and one of the things they did in that workshop that they took us to the lab to see how data that we computational scientists. So we are computational scientists. We
I see.
computational scientists normally do. How they are being generated. So, like I told them a few weeks back, I said that I can't remember the last time I was in the lab. When we are looking at pipette and baguette and all of that. Microscope, looking at things under the microscope. So we deal with data that comes from lab. So our typical lab, have set of computers, high performance computing,
Yeah.
and we work on our laptop really, and we do really. So that's the way. So we have a physical lab. Like I'm in a disease ecology lab. But the
Okay.
funny thing about my lab is that even though it's more of a computational lab, there's also a wet lab part of it. There's a project that some people are doing but I'm not part of those groups. So I'm with the groups that do the computational aspect, where we have a software engineer, we have a
Mm.
data scientist. I am there, a mathematician. We have statistician, we have ecologists, we have public health experts. So it's a disease
Okay,
ecology
let me
where.
let me let me
Mhm.
pick you up at that point. Some of us that go to the wet lab, right? Sometimes your PCR, your your experiment can just decide to like mess you up, and then
Mhm.
you want to run away. Does that actually happen in in your field as well? Like when
Yeah,
what do you do?
So
yeah.
where's the
Experiment
problem?
fails. If I want experiment I'm doing now, I'm looking at the interaction between bird and mosquitoes and how they spread West Nile. There's a disease called West Nile virus that is very predominant in Arizona. So that experiment is still failing now, and I've not been able to resolve it. It's failing.
So when you
So
say failing, what does that mean? Like, is it the equation is not equationing or
uh, let me give you an example.
okay,
I know how an infectious cough should look like.
Mm.
okay,
So you know that an infectious cough, you have a peak and then it goes down, at
Right.
some particular point in time. And then you have this cough that is just going, and it's not really converging. It's not making sense. It's just going, increasing. You don't want the disease to continue to spike. At
yeah,
least
yeah,
not experience COVID. At some point, the cough dropped.
yeah.
So you want to see something like that, and you are not getting it.
Oh,
Like this one, the problem I'm having is that the infectious mosquito population is too high.
Mm.
And it's too high. I'm getting like 20,000, where it should be less than 100. So it's too high. So something is driving that is
yeah,
I've not been able to figure out. Something is driving the population of the infectious mosquitoes. So I'm trying to see how it's going to reduce. So experiment can fail, hypothesis can fail. You know,
okay,
there was a time even though the problem with scientists have is that we think that when it fails or when you define an hypothesis and it didn't work, you are supposed to drop that. No, like okay, there's one paper that will send this month. We
okay,
hypothesize that when we divide into a small scale, like you partition an area into a small scale, that the prediction will be more better. And when the result came out, we discovered that the large scale is still better. Does
mm,
that mean that we'll not publish that paper? No, we'll publish, but we'll just tell them that, the small scale didn't improve our prediction. The large scale is still good. And there might be reason for that, maybe because of the kind of scale, we use. So there might be reasons, and that's what we are even doing in our discussion section
Makes
of the
sense.
paper. So hypothesis can fail, experiment can fail, and that doesn't mean that, you should give up.
Right.
When it fails, you can change your question, but don't
mm,
manipulate data. That's the major.
yeah, yeah, yeah. Mm,
Research
okay,
integrity is very important. Yeah. So,
Yeah,
I have another question for you is like, we have so many diseases that rampant out there, like COVID, flu, bird flu, this and that. But in your lab, what is the process? Like, how do you come up with a particular disease that you select to study? What?
great, great. Earlier this year, I started RSV. It's a respiratory disease, and
okay,
the reason why I'm starting that project is because I discovered that there's an equity question. I
mm,
look at the curve for the black, the curve for the non-Hispanic, the curve for the Alaska Indian, Alaska Native. I discovered that the infectious, and so that means there's a kind of um, equity question we need to answer in that regard. So one of the things we do is that we look at what diseases. Number one thing I say about America is that they do more of project that is useful for their locality, for the American
mm,
population. And so, like Western virus is predominant in Arizona, so and we have data, we have collaboration, and all of that. So we are looking into that because it's predominant. Before I joined the lab, doing COVID today, they were focused on COVID. I am coming up with RSV issue now, which we are going to focus a lot. We're going to focus a lot on it, this year. And another thing we look at, there was a time we discovered that measles and mpox, the epidemic curve is rising. And, we have to, and also now again, that was our last year. Now measles is also spreading
Right.
like
Yeah.
wildfire in Texas. So sometimes we look at the current trend, what's really going out there. And also we have flu. Flu is seasonal. So we do flu. And there's a national flu forecast that happen every year. So we try to participate in. And that's what I want to do for RSV to participate in the national uh, um, forecast. So these are the diseases we look at. We just look at what is really what disease really, is really a global concern or
mm,
a local concern or a national concern. And then we try to see how we can we can model these diseases. And sometimes we look at just gap in literature and then we come up with something.
Yeah. So you try to pick what's relevant, basically,
Yeah.
at the moment. Okay. Yeah, that's one of the functions of science in general. So when you pick a disease, for example, now let's say you pick the COVID. So what next? Like,
Yeah. The
how do
first thing,
you
the first thing you need to do is you need to understand the disease dynamics.
okay.
You need to understand the biology of the disease.
Hmm. Even as a mathematician?
You have to go and read.
Okay. I
Like,
don't believe you
yeah, even as man,
guys.
I have to go and read, look at the transmission rate.
Okay.
You have to do the age stratification. How does yeah, do people lose immunity? Okay, let
Hmm.
me give you an example. In measles, in measles and COVID,
Mm-hmm.
in measles, you can be reinfected, but it takes a very long time for you to lose immunity. But
Okay.
COVID can be reinfected by next week.
Yeah. Yeah.
So that's the biology understanding of the two diseases. So you have to incorporate that in your model,
Hmm.
in your model formulation. Hmm? How long do
How,
people
how would
stay?
you
How long do
incorporate
how long,
just
how long? Yeah, okay. Let me give you the foundation. Okay, let me give you the foundation of
the-
how to model a disease.
hmm.
It starts from Bernoulli. There's a the mathematician Bernoulli is a French mathematician.
Yeah. Yeah.
So he derived an equation that is called SI model, which is called susceptible and infected
Hmm.
model. So since then, those of us in disease modeling, we have built on that model.
Hmm.
Whenever you want to formulate model, you have a susceptible population, you have an infected population. And of course, you can say that, okay, I don't want to go to infected directly. I want to go to exposed population first. People are exposed, but they are not infectious.
Right.
Hmm.
They have the disease, but they are not infected. They can't infect. But then they now move to infectious. Oh, when they are infectious, did they recover? Or
Hmm.
they get to the hospital. When they get to the hospital, did they go to the ICU? Some case can be very critical and they go to the after that, after ICU, did they die
Hmm.
or they recovered? So you can see all those things. So you have to understand the biology before you write, the compartmentalized model, and then you put some parameter, you parameterize it, something that will drive it. Some of these parameters can be the rate can be per day or can be a probability rate, that
Hmm.
must be less than one because you don't want people, a lot of people to die. You can say, okay, death rate will not be more than 0.1, not
Hmm.
0.6, that 0.6, a lot of people might die. So this is the way. So you must understand. So before we formulate any mathematical model for a disease, we try for us read about the disease and how we can parameterize. Some of these parameters comes from the data we have. When we have a data, we have they give us hospitalization data that these are the number of people that are hospitalized. We try to do some calculation. Okay, for
Hmm.
instance, you want to calculate natural death rate because people die naturally.
Right.
There's a way we calculate that. We say one all over. Let me give you this example how we parameterize. So for natural death, we say one all over. The number of days in a year, 365 times what is the life expectancy of that population we are looking at. Let's say for Nigeria, the life expectancy is like I think 70 or so. So you times it by 70, and then you get the natural death. You can see how we
Hmm.
we do all of this. So you see, we have to have the information of the life expectancy of that population we are considering. So this is the way we try to model disease. So we get some information about the population, about the disease. You can see there are a lot of
Hmm.
information gathering that we do first before we now formulate the
Right.
model. Then we start analyzing the model.
All right. So now that I don't know if I should say that Ebola is gone.
No, it's not gone.
But
You
Well,
can see that
now,
one of the things that the argument
hmm,
uh, Elon Musk said. He said he mistakenly removed Ebola fund from
yeah,
US
yeah.
and then they have returned it back because it's. Let me tell one of our takeaways for those people that will listen or watch this podcast is that the world will not be safe if some part of the population are not safe.
hmm,
You get my point? If
hmm,
a disease is still being spread among Africans, it's going to be imported.
hmm,
Yeah.
One way or the other to any country around the world. So when every one of us, we are safe, that's when we can say the whole population, they are now safe. So if you think, and I think that was why Elon Musk, they have to return that phone, because Ebola is deadly. The transmission rate is high. The
Mm.
transmission rate is very high. So it's very deadly. So if somebody can, because one of the things, okay, I didn't talk about that. I normally, I'm also looking at in my modeling technique is movement from one population to another. Movement drives disease.
Yeah.
And how does movement occur? In our model, we can put how people go from a bus station, how people take trains, how people fly. There's
Mm.
a flight, there's long distance movement, there's a short distance movement. Short distance is that you move from your home to grocery store around you, and all of that. So we try to, put all of this in our model, and we discover that movement, you know, travels, they drive. You cannot stop that.
Probably one of the reasons why I think in the past they used to say you should collect enough vaccination before you travel to some countries. So
Yes.
Good.
interesting.
Yeah.
Okay, go ahead.
Yeah. You can ask Wale.
Okay. Uh, y- yeah. So we are now in the section we call the nuance window. So this section is we give you like 2 to 5 minutes to just talk freely about anything on your research topic, on your
I hope political topic is allowed because I like politics.
yeah. You could also talk about definitely you could also talk especially
Yeah.
You can
about
talk
I'll
about
focus
your PhD
more.
too.
yeah.
I'll focus more. Okay, maybe I will talk about science a bit.
But
I don't want
you can
this
talk about
podcast to
politics.
be too serious.
No. But you can talk about politics because
Yeah,
science is affected by politics, obviously. So
yeah.
try,
Um,
yeah, basically.
Number one, our country. I'm from Nigeria. Our country have leadership issues, and we need to tackle that leadership issues. We are messing up, you know, a whole lot. And I think we have an ample opportunity in 2027 to correct the errors of 2023.
Mhm.
Nigeria needs vibrant leadership, strong leadership, young leadership that is focused, and it's not only at the presidency level,
Mhm.
because the local level is also very important. The state level is also very important, and we need to change the dynamics.
I think our problem in
Yeah,
Nigeria is we focus more on federal government.
yeah, yeah.
Yeah.
Um,
Yeah.
and you can't blame them because most of the policy are driven by the federal government. We don't have a kind of a proper federation, kind of, you know, government, so everything is being concentrated at the center, and that's one of the problem, we have. The world must continue to stand with Ukraine. Ukraine has been brutalized. Ukraine has been, they fought a lot of battles over the years, and the world must continue to support them, even if some powerful people in the world think that they don't want to support them again. We need to support Ukraine. Russia is the aggressor. They were the one that attacked that country. And if they succeed in taking Ukraine, means that they can take Poland. I've been to Finland. They are not really far from that. They can take Finland. They can take, uh, a whole lot of. And
Yeah.
it's just the ocean that divide Russia and the United States.
Yeah, in principle.
Yeah, if they continue like that, they can succeed. They will take everywhere. So I think the world needs to support, Ukraine. The Europe must rise up because, we have leadership in the most advanced democracy that, is not interested to help anybody. They are not ready to release money for anybody. So the Europeans should step up, to support one of their own and ensure that, um, the place is safe. And scientifically, for those that still have ambition, your dreams are valid. You can achieve them. I'm an Ikorodu boy, you know,
Oh.
Ikorodu boy that God has
Yeah.
helped, to travel globally. I've been to so many places in the world by
Mm.
God's grace. So if that Ikorodu boy, that boy that was just there in Ikorodu, jumping Molue then, can achieve these feats, and I know that those of you that are, the host of this podcast, you have your story to tell, Isaac Dida, a Lomi boy, you know, you know, he's in the United States doing science. So your ambition, whatever thing you want to achieve, you can achieve it. You just need to keep applying. I believe in apply, and apply, and then yeah, at the end of the day, you get many rejection. It took me 3 years for me to be able to get a scholarship to go and do my PhD, and because I was determined that I want to do this PhD, I was like, I'm tired of reading. I want to be a global citizen. I want to be an international person. That's what I want to be. So I was yes, I have the ambition. I want to be an international person. So I was pursuing it. So you must pursue it. I've heard a lot of stories about people and it's doable. There's a boy I mentor, he was just there in the East doing his BSc in law, doing a bachelor's of art in law. So what do they call it? Or I don't know, should be LM, whatever. I don't.
LLB, yeah.
LLB,
Is it LM? No, is it
LLB,
LMB?
LLB,
LLM, the masters. Or
LLB,
bachelor, huh?
LLB.
LLB, yeah. Thank you, LLB. And it was just there. Do you know that with guidance, with all of that, this boy did not even go for his NYS and he got a scholarship in Missouri here in the United States. Young boy, vibrant, brilliant. Yeah, he got away with the first class. He didn't even go to law school because he has this vision. We started this application, immediately got to his final year of his law program, not law school. He didn't go to law
Yeah.
school because he
Was
said
it
he
first?
doesn't want to be a lawyer in Nigeria. He wants to come and be a lawyer in the United States. He has that ambition. And he pursued it and he got it. And it's currently in Missouri. So we must, continue to push whatever thing. Yeah, the environment of our country, we don't have data, we don't have light. All those things can constrain us. But we must keep pushing,
Right.
keep believing, and the sky is just our limit. It's not to motivate you. I'm not a motivational speaker, but it's doing. Yeah,
Yeah,
because we have a real life example in this
yeah.
podcast. Myself, Isaac Adewale, we are here, and also an example I just started. And there are many more examples that that
I,
we have.
I I have a friend that used to be an Air Force. I think Dr. K knows him. He used to
Mhm.
be an Air Force officer
Yeah.
for 18 years. Then he's in Boston now doing his PhD. So
Mhm.
that's that's an example of someone that didn't give up on their dreams. And even
Mhm.
though he was serving as an Air Force guy, he had to travel. He told me he had to travel from Maiduguri to Kaduna just to go to school. And he's still in
Just to,
Kaduna.
Wow.
Yeah.
just to go to school,
Yeah.
so that you will have a BSc that I can use.
Hmm.
I graduated with 4.99 something or so.
Wow.
So just to achieve his dream. And then he's out. He's in Boston, doing very well.
Yeah.
Richard and Ope,
Yeah, it's true. It's Richard.
he's balling now.
Richard, he has been in trenches.
No, don't mind him. Yeah, so yeah, so that's my thoughts, and I think let's keep believing, let's keep working hard work, and the God factor is also there.
Yeah.
God, it's God that does all things. I'm not a pastor, but I know that
Dr.
is
K,
God.
I have a last question for you before we end up this podcast. Like I want to go back to the Ebola question, right?
Mm,
Learn some things in Ebola, and we know that Ebola is not gone, but we have a particular disease that is still very rampant in Nigeria, which is malaria.
mm.
I think we can transfer what we learned from your Ebola study to malaria
Hmm.
because malaria has killed a lot of people, honestly.
Hmm.
Yeah, thank you for that question. The way you model Ebola is different from the way you model malaria.
Mm,
Malaria, there are two things that are important in malaria transmission. You must have the mosquito population
mm,
and then the human population. And there must be an interaction between the two because the mosquito bites human. So there's what we call bite rate when you are modeling that. That is not in Ebola. Is just an infectious, disease, So of course we can learn some things there, but it's not totally applicable,
mm,
to malaria. And you cannot cure Ebola with sanitization. One of the preventive measures I can put in in a malaria model is sanitization because stagnant water breed mosquitoes.
Mm.
All these our trash that we don't trash, they breed mosquitoes. But for Ebola, that's not the case, It's not the case. So hygiene and all of that is very important when it comes to malaria. Malaria is not endemic. It's not endemic in our population. And there are ways we can tackle it. There are different models. I think I also have a model of malaria. I think it's still under review. I think I have not published that work. There are different models on malaria, but the basic thing and what we have suggested over and over again, you cannot eradicate malaria, reduce mosquito population when there's no proper uh, um, um, waste management. We don't have what do we call all this gutter thing? There's a name for it.
Drainage.
Drainage, yeah. No proper drainage. There's still a lot of standing waters. One of the things I've seen when I've modeled mosquito population, standing water drives mosquito. There's a lot of standing waters. There's a lot of waste around us. So if we don't tackle all of those problems, and like what Opa said, malaria is deadly. It kills. But people don't know that I think there's what we call there's a type of malaria that I think it's cerebral malaria also.
Yeah, yeah.
They are deadly. So they kill, but we think that we can treat it any small thing. We say malaria, malaria. No. We think malaria is just malaria like that. Malaria is a very deadly disease. So there are very little things we can learn from Ebola that we can transfer to malaria model, but it is a different type of mechanism. Ebola doesn't have a mosquito population. We need to, when we are modeling malaria, we need to consider the mosquito population. Ebola, might not have a relationship with an environmental factors, but when it comes to malaria, you have to look at the environmental factors. There are a lot of environmental factors, rainfall, temperature, everything that drives, mosquito population, and then they bite the human, and transfer the disease. So another thing we normally use to tackle malaria is insecticide, which if you go to literature, there are a lot of people that said, okay, the use of insecticide, how does it, reduce the spread of malaria? We don't use insecticide for Ebola. So you can see that the dynamics of this disease, they are different, and yeah. So, but there are very few things we can learn from Ebola that and then I think also there's no evidence. There's no evidence that there's an human-to-human transmission in Ebola. I mean, in malaria. But in Ebola, there's an human-to-human transmission, So you can see the different dynamics. So,
Is there any speculation that there could be human-to-human translation of malaria?
no. There is none, but who knows? Maybe this disease might evolve one day and then
Okay.
it can be. And then, okay, let me give you an example. One day, maybe malaria will evolve that there will be a sexual transmission. It's going to be like we discover for, let me give you an example. We discover for,
problem.
we discover for mpox. Do you know that there's a lot of spread of mpox between men that have sex with men and women that have sex with each other? This what's it called? LGBTQ thing. So if you go if you Google about sexual transmission in mpox. So mpox evolved. It was not like that. So when mpox started, it was not like that. But it evolved that we discovered that it spread more when we discovered that men that have sex with men, a lot of them were having, mpox. So, which is one model we have considered. And I was still looking at that paper this morning, So this is some of the things that happen. Diseases evolve, they evolve. Now look at bird flu. Bird flu dynamics is changing now. The way bird flu is now, if you are reading the news, the bird flu dynamic is changing. It's changing. The kind of transfer that was not happening before is happening now. So we need to be,
Yeah, because you mentioned vaccine now, I think I've gotten to the end of my question, but I don't know. See, we are not talking about politics, but this is my last question, I promise. Like our current secretary anti-vax. So what?
Because we are in a regime of anti-vax, so anti-science, anti-vax. So
what do you think about that? Like, do you think people should still be vaccinated or?
I strongly believe in vaccination. It helps. It helps. I think that's one of the conclusion of my PhD thesis. It helps us in the COVID-19 spread. Vaccination helps. The recent measles, I was looking at Texas Human Health Services data yesterday in terms of measles. We discovered that very few of the cases are vaccinated.
Oh,
A lot of
wow.
them are not vaccinated. There is measles vaccine, but because even the person that is the current secretary of Health Services of Nigeria, of United States, has preached against vaccination, so those are the problem we have. Of course, some people there are a lot of misinformation or disinformation, as the case may be, that is the one causing Down syndrome. There's this other thing that is very common now.
Autism.
Autism is causing autism and all of that. I was telling my wife one day, I said, when we were young, we say, they will call it Abaya Jesaka or whatever. We take it innocently. Are we not healthy?
Yeah.
We don't have we don't have any information.
I don't even know. Yeah.
The, our eyes were so blind there. We don't have any, and we still go to get those vaccines. We take it here. We do all those things. And are we autistic? So, and this disinformation, there's a theory we normally say, please remind
Conspiracy theory.
conspiracy theory, up and down and all of that. So this is not helping us. And that's one of the things we are considering in our modeling approach. How misinformation drives, the spread of disease.
Yeah.
It's a whole lot. I strongly believe that vaccine is good. My vaccine is up to date. Yes, my vaccine is up to date. In fact, I'm going to take one shot again for 2 sets of vaccine, the last shot in April. So it's and we're healthy.
Yeah.
So all this disinformation, I believe so much in those. I believe in science. I
Yeah.
think it's those people that doesn't believe in science that they're against all of it. I strongly believe in science, and I believe that vaccination helped us in COVID. It helps us a lot. It helps us to open up everywhere, and it has helped us. Polio. Look at Nigeria. It has helped us in terms of polio. I think we are now. I think we have eradicated polio. I think so. Maybe it has come back. There was a time they gave us a clean bill, but maybe it has come back. And what helps us with that? Is not vaccination.
Yeah.
And
That's
you tell me that I should not believe in vaccination? No, no. I will not. So even the current, even that has preached Kennedy Jr. that has preached again, he agrees that the vaccine of measles has helped, to drive measles out. But now, because people don't want look at what they have cost, the case is very terrible in Texas, and I'm very sure that they're going to import it to other neighboring states and some other, country. When last did U.S. experience death due to measles? It was 10 years ago, and it happened this year. So, and what helped them in those years?
vaccines. Yeah.
Vaccination.
Yeah.
Vaccination.
Yeah. Thank you so much for answering that question. I think we have come to the end of our questions for today, and we really appreciate you for coming to our podcast, and we are truly grateful for you sharing your experience in mathematical modeling, infectious disease, and I hope that people that are watching these videos, they will be able to learn a lot of things. The summary of what we talked about is how mathematical modeling help us to understand infectious disease. Then we talk about a bit of politics, and also talk about how you should not give
You
up.
can't have me on your podcast. I will not talk politics. Maybe there will be another day that will do just purely politics.
Yeah.
No
Okay.
science, because people know that if I don't do science, I will do politics.
To
Yeah.
attack
But
the
now I don't have flair again for politics because of the situation of the country. Really, I was very passionate and all of that, but now I don't. I just comment and yeah.
Well, you could go back home and combine the two.
I don't know. I don't think I will do that again.
Okay.
I don't think so. I don't think so.
They are
I will
disappointed that
encourage people like Okpa to do
they don't need good people in Nigerian politics. So that's what.
that.
Yeah, but we really appreciate you. So I don't have any more questions. I don't know if Wally has something to say. And so we've come to the end of the podcast. We are truly grateful once again, and we hope you stay safe. And we hope you continue to enjoy